This video is about inverse trigonometry, and it can be found in your text in both sections 8-5 and 8-6. Let's stop for a minute and think about what an inverse even is. So you are familiar with several inverses already in math. For example, suppose we start out with a number 2, we multiply that by 4, we get 8. Then if we take 8 and divide it by 4, we get back to where we started, 2. So an inverse of an operation brings us back to where we started. This man walking backwards is kind of a visual for you about that. Okay, what about adding and subtracting? Suppose we start out with the number 5. We add 3, we get 8. We keep the number 8 and subtract 3. Magic. We get back to where we started, 5. So adding and subtracting are inverses, multiplying and dividing are inverses, and trigonometric functions like sine, cosine, and tangent also have inverses. It might be confusing you that I'm using the word function, but a function is just something that attaches one quantity to another related quantity. So a function of an angle is the tangent of that angle. That's a function of 1 degree. The tangent of 1 degree would be 0.0175. So the inverse of a trig function can get us back to where we started. Suppose we started out knowing that the sine of 5 degrees is, here it is on our table, 0.0872. So how could we start with this number and get back to where we started? Well, we call it the inverse sine of 0.0872. And we write it like this. It kind of looks like we're writing sine to the -1 power, but we read it as the inverse sine. The inverse sine of 0.0872 is simply 5 degrees. It's like we're walking backwards, getting back to where we started. So what's the point of having inverse trig functions? Well, so far in our problems, we've been given side lengths and angles and asked to find another side length. But what if we're asked to find an angle without any of the angle chase tricks that we already know, like vertical angles, some of the interior angles of a triangle? Notice that none of those things are going to work in this triangle. We have a 90-degree angle and we're asked to find y. But we really don't have anything to work with here because we don't have any vertical angles and we don't know what this angle is over here. So trig can help us find what this angle measure is without having any other angle information here. We can use the sides of this right triangle to find out y. Let's do an example. We're asked to find y to the nearest degree. So we have a right triangle. Y is one of the angles. We don't have the opposite side measure, so we're not going to use a trig function that involves that side. What we have is the tangent, and we have the adjacent leg. So the best trig function to use in this case is cosine, because the cosine of y is information that we already have. The adjacent leg, 2, over the hypotenuse, which is the square root of 13. Now, we're not going to worry too much about the fact that a radical is in the denominator, because this is not our final answer, and we don't have to simplify this right now. What we can do is plug this into our calculators. If you have a scientific calculator, you may be able to do this all in one move, but the safest way might be just to find the square root of 13, plug it in for this denominator, and then do 2 over that number. Either way you choose to do it, you should come out with the same number. So we have the cosine of y equals a number that looks like 0.555 4, 7, and then some zeros and other digits after that. So because our trig table only has 4 digits after the initial 0 point, we're only going to deal with the first 4 digits here. And since this next digit is a 0, we can round down. So we're just going to round it to 0.5547. That's the cosine of y. All right, we know what the cosine of y is, but what's y itself? We're going to have to use our trig table backwards in this case. So we're going to go to our cosine column, and we're going to search down in here until we find a number that's close to 0.5547. Okay, I see 0.57 something. Look, here's 0.55 something. That's pretty close. That's about as close as I'm going to get in this trig table. So there's my number. Then I'm going to go backwards over to the angle column. And I see that my angle that would have a cosine of 0.5592 is about 56 degrees. That's my answer. You try one like this. Find y to the nearest degree. Let's do another example. This time we're going to have to draw a picture. We're told that the grade of a road is 7%. Well, what on earth does that mean? Let's make our road, and if a road has a grade, then there's part of it that goes uphill. And 7% is the amount that it goes up divided by the amount that the road surface goes over this direction. So 7% is the same as 0.07. It's also the same as 7 hundredths. That's the easiest way for me to think about it. So what angle does the road make with the horizontal? I'm going to use y again for the angle, y degrees. We're asked to find that angle. So we have a right triangle here. We have 7 on the opposite side and 100 on the hypotenuse. I like to circle my hypotenuse number. That reminds me that I definitely can't use this 100 as the adjacent leg. The adjacent leg would be right here in this triangle. Okay, so what angle does it make? We have the opposite side and the hypotenuse, so the most convenient trig function to use is going to be the sine function. We have sine of y equals 7 over 100, which is the same as 0.07. Now, we know what the sine of y is, but we want to know what y is, y itself. So again, we have to go backwards. We're going to look in the sine column, and we're going to go down until we find something close to 0.07. I have 0.05, 0.06, 0.08. Wait, if I back up to here, it looks like I could round this to 0.07 if I was just going to the hundredths place. So this is my lucky winner. And I'm going to go backwards to find the angle that corresponds with this sine ratio. My angle is 4 degrees. So I've found out now that my angle y is 4 degrees. And that's the angle that the road makes with the horizontal. You try one like this. The grade of a road is 16%. What angle does the road make with the horizontal? Let's do one more example. Here we're asked to find the values of several angle variables. Notice that this isn't quite as scary as it might look at first because we have 2 congruent angles. They're both labeled with a measure of v degrees. 2 congruent base angles tells me I have an isosceles triangle, by the way. That may not come in handy, but I'm going to mark it anyway. In this type of situation, I want to use trig because I'm being asked to find angles and I don't know what any of these angles are. So I can't use my old moves like internal angles of a triangle. I'm going to drop an altitude. We call this an altitude if it's a line that's perpendicular to one of the sides. And by isosceles corollary 3, which is coming in handy a lot these days, we know that this part and this part of the base are congruent. So if the whole thing is 16, then I have that this part is 8. Now I have a right triangle. I know two sides, and I'm looking for an angle. So that situation is something we can deal with using inverse trig. Okay, V is my angle in question. I have the adjacent leg, and I know the hypotenuse, which is directly across from the right angle. So adjacent and hypotenuse, what would be the most convenient trig function? I'm going to choose cosine. The cosine of V is equal to the adjacent side, 8, over the hypotenuse, 10. And that's an easy number. It's just 0.8. So I have the cosine ratio, and I'm looking to find the angle. So I'm going to need to go backwards. Cosine is the middle column in my table here. I'm going to go down, down, down until I find something close to 0.8. Okay, this number looks promising. Looks like that would round to 0.81. This number looks good too, 0.79. And look, this third decimal place is so high that this would round the whole thing up to 0.8. So I'm going to choose this as being the closest to 0.8. I know the cosine. I'm going to go backwards to find the angle itself. And my lucky winner is 37 degrees. V equals 37. Okay, am I finished? Not quite, but I'm pretty close, because now I know the two base angles of this big isosceles triangle. So I can use one of my old tricks to find out what the remaining angle is. I can use IATs. So I have that W is equal to 180 minus 2 times the measure of angle V. So I have 2 times 37 degrees. 180 minus, this comes out to be 74, so I have that W equals 106 degrees. You try one like this. Find the values of the variables. For further practice, see page 308 of your book, numbers 7, 9, 11, and 21. Also see page 314, numbers 7, 9, and 11.